हमारी डिस्कशन जो है वो हो जो आपने मैकेनिक्स ऑफ सॉलिड 1 जो है उसका मैंने रिव्यू करवाया था। उसमें एक चीज जो है, एक करेक्शन एक जगह पर जो है वो मैंने की है। ठीक है, वो मैं पहले आपको जो है वो बताना चाहता हूँ, फिर हम आगे जो है वो मूव करेंगे। ठीक है, हमने जो ओके ओके ओके, so you'll have to remind me, dear foreigner, what is your name? If I'm
Abdullah Ibrahim, sir.
okay, if I'm speaking in Urdu, then you'll have to remind me. Okay.
Okay, sir. Even I was going to remind you, but I'd say the teacher is starting by Urdu, then he will explain in English. That's why.
Okay. Okay, so we are discussing mechanics of solid 1 at a glance, and at that time, did you start recording? Yes. Okay. At that time, we discussed this slide in which we talk about this negative sign, and there was mistake, so I've mistakenly placed a negative sign here also. So actually, there is no negative sign with the moment my. Okay, this negative sign is basically equilibrium requirement and the stress requirement, the convention requirement, actually. Okay, so with this negative sign, the sign convention is okay as per the Cartesian coordinate system, that if moment is about the positive z-axis, then it is taken positive, and y along positive z-axis is taken as positive, then there must be a negative sign. But for the moment about y-axis, without negative sign, the convention is okay. The convention for stress is okay. Okay, so my should be taken positive about my, and z should be taken positive in the positive z direction, and this is our positive z direction. This direction is our positive z direction. Okay, so this was just you'll have to correct this now, and we also discussed the geometric properties, and geometric properties are very important. You should be able to calculate the cross section area, to locate the centroidal axis, to calculate the moment of inertia about any axis, and to calculate the product of inertia. You should be able, without these properties, you will be unable to solve any kind of a real life problem using the mechanics of solid theory. Okay, so you need to know and you need to be familiar with these geometric properties. Okay, now coming to the combined stress. Combined stress is just a name indicate that this is a combination of multiple stresses. Okay. And I've written a statement on a particular plane, normal stress and shear stress do not interact with each other. Okay, on a particular plane, this we'll talk about later on. Okay, while discussing the stress transformation, so we'll talk about this on a particular plane, because in some other plane they may interact with each other, but on a particular plane, just like this shaded plane is a plane, if a number of forces like causing shear stresses, normal stresses are acting on this plane, then they do not interact with each other. Okay, so normal stress and shear stress do not interact with each other. Now, so since they do not interact each other, so you can separate them. These are the forces causing normal stresses: the axial force, the bending moment about z-axis, and the bending moment about y-axis. And these are the forces causing shear stresses: the torque about x-axis, the shear along z-axis, and the shear along y-axis. Okay, so I've separated them, and the stress is produced at a certain section can be obtained by combining the stresses obtained by the individual forces as per the principle of superposition. So this is this px divided by a is the stress caused by the axial force px, mz divided by iz into y, this with a negative sign, as I'll talk about just a while before. So this is the stress caused by the bending moment about z-axis, and this is the stress caused by the bending moment about y-axis, and this is positive and this is negative. Okay, so this is the combined stress formula for normal stress. There are three kind of forces, px, mz, and my. They are causing normal stresses, and if you want to get, so this is the formula, and if you are using these signs, Okay, and signs of the px, like if px is tensile force, it is written as positive, and px is compressive force, then it is written as a negative number. If mz is about positive, z axis it is taken as positive moment vector I'm talking about. And similarly, if my is about the positive y axis and y vector is along the positive y axis, then it should be taken as positive. Okay, so this will automatically recover the sign, and y and z are as per the Cartesian coordinate system. Y is positive along the positive y axis and negative along the negative y axis. So it will automatically control its sign, and finally this whole relation will result in a number, and that number, if positive, then it is a tensile stress. If it result in a negative number, then it is a compression stress. Okay, similarly you can combine these forces, these stresses. Okay, these stresses, you can combine these stresses. So the you can combine stresses. Stress is a tensor quantity. It is one step ahead of the vector quantity, and the rule is applicable to this to a vector quantity, also applicable to this, and some more rule are applicable. Like if you just talk about this one, like if you have a shear force in this direction, okay, and if you have a body, like if you have a normal force in this direction, then they do not interact with each other, though they are in the same direction. If you have a stress in this direction and a normal stress in this direction in a certain body, then they do not interact with each other. Okay, they are in the same direction, okay, but they do not. But if they are of the same kind, then they interact with each other. Same kind mean if they are shear, then they will interact with each other. So this Tx is causing stresses in a tangential direction, like its direction changes as you move around this x-axis. Okay, so this the direction of the stress changes here. Like if I'm talking about this point, so the stress direction is horizontal, like in this direction. At this point, the stress direction is like vertical in this direction. Okay, so this Tx is causing vertical as well as horizontal stresses. This Vz is causing, like Vy is causing a stress tau xy. This x, as I've already told to you, that it represents the plane on which the stress is acting. So this shaded plane is the x plane because its perpendicular is x. So tau xy, so this is x plane, so on the x plane in y direction. And this is causing, this Vz is causing stress on x plane in z direction. Okay, and this torque is causing both stresses in y and z direction on x plane. So you can combine these stresses. Okay, you can combine them, but you cannot combine this with this one because they are perpendicular to each other. Okay, so you cannot combine, but you can combine stresses in the same direction. Just like we did combination for this case, because all of them were causing stress in the x direction. So you can combine this with this one, and you can combine this with this one. So this is the combination. Okay, so this is the combination how you can combine the stresses. Okay, now this is a very good example of the combined stresses, and it will give you some insight into some actual situations. So let me first read the statement of this problem. This is problem 902 of your book. Compare maximum stress in bend rod. Bend rod, you can see this is a bend rod, a half-inch square, where the rod P where the load P is half-inch off center as shown in the figure. This load, the bend is such that the line of application of load is half-inch off the center. Okay, and he is asking to compare the stress in this bend rod with the stress in this straight rod. Okay, the case is same, but only there is a slight half-inch bend in this rod. Okay, and you'll have to, he's asking just to compare the stresses in this case. And let's first do the example, and then we'll talk about the practical application of this. He's also saying this problem illustrates why the lateral deflection in column is so dangerous. Okay, the lateral deflection in column is so dangerous. Okay, So we'll talk about this one. From the free body diagram, just first talk about this case, this bend rod. So if you cut this, and this is the left side of this, so this is the free body of the left side. Okay, you have cut it here. So if you just apply the equilibrium condition to this one, I'm applying directly the equilibrium condition. I'm not writing that sigma fx is equal to 0 and this is equal to this. I'm not doing it like this. Okay, I'm directly, because the objective is not to use the equilibrium condition. The objective is to solve this problem. So you'll have to concentrate on this one, and other steps you can do it directly. Okay, there is no need to write much explanation for this one. Okay, so this P horizontal, sum of the horizontal force should be equal to 0. So there is a force here, so there must be a force applied at the centroid of this cross section. Okay, so they must now this bar is balanced for forces along x-axis. Okay, now these are two forces, they are not exactly in the same line, so they are creating a couple, equal and opposite forces, and the moment arm is half inch, so they are creating a counterclockwise couple. So this is not a balanced thing, so you need to apply a clockwise couple equal to this moment. Okay, a clockwise moment, so this is P into half. You will have to apply so with the application of this moment, this whole thing is now in what? In equilibrium. Okay, this whole thing is now in equilibrium. Okay, here I've written, this is the cross section of this. I've drawn the three-dimensional view of this one. So this is the cross section of this one. This is, he's saying this is half inch and this is also half inch. Okay, so it is subjected to an axial force. I have written this is Px as a positive force. Actually, this is a negative force. So Px, I've written it as a positive. Okay, and there is a moment about z-axis. The moment about z-axis here, if you just use the finger of your right hand, if you rotate the finger of your right hand in the direction of movement, so your thumb will point in the negative z direction. So this is a negative moment. Okay, now as as per the sign convention, this is also a negative moment. If you just if you are taking a moment to the right of a section, okay, and if that is a clockwise moment, so that clockwise moment is considered as a negative moment. Okay, so this is a negative moment, and so this section is subjected to an axial force Px equal to minus P, and a bending moment equal to minus P into half, meaning minus P by 2. Okay, minus P by 2. So this section is under combined stresses. One is the axial force, the other one is a bending moment. Okay, there are two kinds of forces acting on this one. Okay, now each problem of the mechanics of solid, in each problem you will have to do two things. You will have to calculate the forces acting at a certain location or the required location, and you will have to calculate the geometric properties of the cross section, the required geometric properties of the cross section. Now here you have the axial force and the moment about z-axis. These are the only two forces acting on this cross section. Okay, so you need to calculate for Px, you need to calculate the cross section area, and for moment about z-axis you need to calculate the bending moment about z-axis. And since this is a square section, so there is no need to locate the centroid because centroid is already located. So Iz the cross section area is half into half. This is a half inch square, so this is 1 by 4 square inches, and the moment of inertia about z-axis is half into half cube by 12, so this is 1 divided by 192 inch power 4. So this is the moment of inertia above z-axis. So we got the geometric property also, we got the forces and geometric properties. Now you have the combined stress formula, that sigma x is equal to Px over A plus mz divided by, with the negative side, mz divided by Iz into y. And since I'm y is 0, so I haven't written the my value. Okay, so just plugging the value, Px, just write minus P divided by 1 by 4, and mz is equal to minus P by 2 divided by this one. So if you just simplify this one, so sigma x is equal to minus 4P plus 96Py. Now, this is known as a stress equation or the fiber stress equation in this case. Okay, if you have bending moment if only about one axis, and then this is known as a fiber stress, because this is giving you stresses along a certain fiber. Okay, so this is a fiber stress equation. Fiber stress equation. Okay, putting the value of y, this equation will give you stresses at any location in terms of p, since p is just an unknown in this case, is just a number. Okay, so this is the fiber stress equation. Now, for the neutral axis, though this is not required, this is not the requirement to locate the neutral axis, is not the requirement of this problem, but I'm locating the neutral axis. So for the neutral axis, the stress should be equal to 0. So just plug in stress equal to 0 in the same equation, just in this equation, make it equal to 0. So this will give you a certain value of y, and that is the y neutral axis is plus 1 divided by 24 inches. Okay, plus 1 divided by 24 inches. We'll talk about this whole stress variation diagram, but the neutral axis, in this case, the neutral axis, this is the neutral axis, and the neutral axis has shifted upward. Plus mean in the positive y direction, so plus 1 divided by 24. So it in the case of pure bending, we know that the neutral axis coincides with the centroidal axis, but in the case of combined stresses, the neutral axis do not coincide. The neutral axis do not coincide with the centroidal axis of the member. Okay, so this is not necessary that the neutral axis coincides with the centroid of the of the section. Okay, so in this particular case, it has shifted upward. Now, stress at top and bottom fibers. Now we're going to calculate stress and top and bottom fibers. So in the top fiber, like this fiber or this fiber, this is a complete fiber. Okay, so in this fiber, the value of y is what? This is total is half inch, so this half is 1 by 4 inches. So just plug in plus 1 by 4. Okay, so in the previous equation, so you will get plus 20p. So it means that in the top fiber you will get tension, and from the common sense, if you are applying this force, so obviously you will get here tension. Okay, and in the bottom fibers, if you plug in minus 1 by 4, so this will give you minus 28. Now, this whole thing is, if you are using the appropriate sign, the proper sign convention, that then the stress will automatically give you a proper sign. In your book, you will have to manage it yourself. In your book, the Singer book, it is not given like this, so you will have to manage it. He is writing plus minus, so you will have to yourself, you will have to decide that is this positive will result in a positive, a particular value. He's writing this equation like plus minus p over a plus minus mz divided by iz into y. Okay, so you'll have to decide yourself, but here the formula decides the signs itself. Okay, so this here in the bend bar, you have the maximum stress of out of these two is minus 28p. Okay, so this is the maximum stress, and the maximum stress will be at this point. This, you can see the pointer or this fiber. Okay, the bottom fiber. Now, if there is no bend in the rod, and if the rod is straight, and if you take a free body of this one, so this rod will be just subjected to an axial force. Okay, only axial force. So in this case, the stress is saying max is equal to px over a minus p. So this is minus p divided by 1 by 4. So this result in minus 4p. Okay, so here you can see the stress is minus 28p, and here the stress is minus 4p. Now if you just take the ratio of, so comparison mean, if you take the ratio, so 7. So the stress in bend rod is 7 times more than that in this rod. Okay, so you can imagine that how much high stresses are creating. Let's suppose if in the straight rod the stress created is let's suppose 500 psi, then in the bend rod the stress created will be 3500. It's a very high value, 7 times of 500. Okay, so 3500, it's a very high value. Usually we do have in our design, we do have a factor of safety like 2 or 3. Okay, in most cases we do have a factor of safety of 2. So if you have you haven't considered this eccentricity. This is known as eccentricity. This is the amount in which this rod is bent, or this is off the line of application of the load. So this is known as eccentricity. If the eccentricity is not taken into account in the design, that it will result in the failure of the member. Okay, because the safety is just a 2 time, and here you are exceeding stresses by 7 times, so it's a very high value. Okay, we'll talk about this the practical application of this one, but let's first talk about this stress variation diagram. Okay, this is the stress variation. The stress is in the x direction, remember, just perpendicular to the cross section, not like parallel to the cross section. This is perpendicular to the cross section. Okay, so this is the stress caused by the axial force. If you have just the axial force applied, so we know that the stress is minus 4p. So this is a compressive stress. And if you have just the bending moment applied on the section, there is no axial force, then the stress variation will be this one. Like you will have this, you will not have this component, you will have just this 96p divided by y. Okay, so if you just calculate the stresses in the top and bottom fibers, if you plug in the value y equal to 1 by 4, okay, so it will result in plus 24. And if you just plug in just ignoring this one, don't consider this one, just assume that only bending moment is applied on this section. Okay, so this is the stress variation diagram. In the top plus 24, in the bottom minus 24, and the neutral axis coincides with what? With the centroidal axis of the member. Now if you combine this one as per the superposition principle, okay, this is the axial component, this is the bending component. If you combine both of them, so it will result in a stress variation like this. If you just minus 4p plus 24, so it will result in plus 20. If you combine minus 4p minus 24, so it will result minus 28, which just like same in this case. Okay, now the stress here in the neutral axis is 0, but there is a stress of minus 4p here. So in the centroidal, at the centroidal axis, the stress is not equal to 0. It is rather, it is equal to minus 4p, equal to the axial stress. Okay, so this is not 0. This is equal to minus 4p. But if you just move slightly upward, so there is a stress minus 4p, and there is a location where there will be a stress of minus 4p here somewhere. So if you add both of them, it will result in a 0 value. So this is the stress variation diagram. Okay, this is the stress variation diagram in which you can see that the neutral axis has shifted upward by an amount of 1 by 24. Okay, so if we can draw this stress variation diagram like this also, like we can draw this stress variation diagram like this. This is also a way to write the stress variation diagram, that if you have this as a compressive force, this is towards, okay, and this is a tensile force that is away from the cross section. So this is also one way. Or if you just take a mirror of this triangle, so it will result in this thing. Okay, but this one is helpful in the case if you have stress here and stress here, join both of them, so it will automatically give you the neutral axis location where the neutral axis lies. But in this case, you will have to, like if you want to draw it, so you will have to first locate the neutral axis, and then you can draw the stress variation diagram. Okay, so this is how to draw the stresses, the stress variation diagram. So we don't need this diagram. This is not the case. We need this diagram or this diagram, okay, in which the actual neutral axis is shown. Now, so this is the case. Now let's come to this 7 and the practical application of this one. So if you have a column, okay, a column, this is a half-inch square column, so its dimension is also very small, and this is bent like half-inch, equal to the cross section of the member. Okay, so what is happening? The stresses are increased by 7. Okay, so 7 times increase in the stress. Now if you have a vertical column, Okay, and let's suppose practically, usually the column size is like 12 inches, 15 inches, 18 inches, 24 inches. These are the usual sizes of column, and the height is usually from 10 to 12 feet. Okay, and if you have a column of 12 inches, and if there is an eccentricity, there is a bend in the column equal to 12 inches, which is practically not so much possible. Practically, the eccentricities are not so high. The eccentricities are sometimes in the range of 1 inch or 2 inch or even less than this one. Okay, but still they cause very high stresses, and you will have to avoid those kind of eccentricities in the member. Okay, eccentricities in the member, you will have to avoid those things. Okay, so if you have this kind of a thing, then there will be, if you are designing and if you are not, and these are the practical imperfection. You are during construction, there is a possibility that your formwork may move to one side. Okay, and when it moves to one side, so the stresses are higher at one side and the stresses are lesser at the other side, and there is a possibility that the high stresses may exceed the strength of the material and there could be a failure. So if it happens, and usually it happens in many of the public sector projects, and if you have certain, let's suppose you are a supervisor and you are supervisor and a site engineer for a work, and you come across such a situation that there is a column of 12 inch by 12 inch, and when you just check the plumbness of the column, so you found that the column is, let's suppose, 1 inch out of plumb. Okay, due to the movement of the formwork when during casting. Okay, so what will you do? So there is one possibility that you order the contractor just to demolish the thing and reconstruct. Okay, but it has a very high cost implication. Okay, now sometimes this column may be in the intermediate floor, so he cannot remove the column, he will have to remove the whole thing. Okay, so there is another possibility that you just check with this eccentricity, you can check the design and if it is within certain permissible limit, that the stresses are not exceeding the strength of the material, okay, or the capacity is still within the demand is still within the limit of the capacity, then you say it is okay, you just find the contractor with a certain amount, because this is a mistake and he should do work as per the standard and specifications. Okay, so you just find the contractor and you say it is okay, it is acceptable to me, do nothing, and just fine is for that next time he's very careful. Okay, the next is, if there is, let's suppose there is a problem. Okay, the stresses are exceeding the limit at the design load, so what will you do? Okay, so one thing is just remove, so it's very easy just to say remove the thing, but sometimes it's very difficult. Okay, so there are then possibility that you just talk about some repair, retrofitting of the structure. Okay, just to do this thing and this thing with this one, so it will be safeguard. So just treating that element, and you can improve the capacity of the member. Okay, and there is one thing, it is said usually in Pashto, the vertical element which is given as a support to the roof is known as a stun. Usko stun bolte hai, the needle. Okay, and needle is also used for the for sieving. Okay, for just to sieve your clothes. So needle is also required for that one. Okay, so in Pashto it is said, I'll have to talk in Pashto. So it is said, stun why the stun joda ka khushi de joda ka. The stun joda ka khushi de joda ka. It means that if you want to erect a column, so okay, its cross section should be as small as the cross section of a needle, but keep it straight. Okay, keep it straight. If it is not straight, then it will cause some big problems. Okay, usually you might have come across the form work which is which is made for the casting of your roof slab. So the formwork is supported using wooden logs or lodges, and those wooden logs are what they are. They are like they are not straight. They have some big eccentricities. Okay, so they might cause some serious problem. Okay, while if you are causing the concrete, so they are then coming under stress, and there might be some serious problem. Okay, so what if your contractor is an intelligent guy and he has some engineering sense? Then he do what? He just combines some vertical element with a horizontal strip, and in this way he can control this lateral movement of the member, and he can control the stresses produced, the excessive stresses produced in the vertical supports. Okay, so this thing this is a very good example. Okay, and of the various engineering problems, and we'll talk about the columns, the columns and the stresses produced in the column, the secondary effects, and all these things in our in a course of the midterm. Okay, this is next problem, problem 904. Problem 904 is to avoid interference. A link is in a machine is designed so that its cross section area is reduced one half at section AB as shown in figure. So here you can see that this is a link which is used to transfer a force from one location to the other location, but due to some interference, its cross section at this location is reduced to one half. Here the cross section is like 80-meter high, but here the cross section is 80 millimeter high. Here the cross section is 40 millimeter high. Okay, and its width is the dimension which you cannot see here is 50 millimeter. If this is the cross section, then this is 50 millimeter and this is 40 millimeter. So he is saying compute the maximum force that can be applied if the maximum normal stress on section AB is limited to 80. So he is limiting the stresses to 80 at this location, and he is saying how much force you can apply to this section. Okay, so in this case, stress is given to you, and you will have to calculate the P, the force applied on this section. Okay, so just like if you cut, this is section AB. So if you cut this, the link here, and draw the free body of the left side. Okay, so horizontal force equilibrium requires, now the centroid of this cut section is here. This is also a rectangular section here, you can see. So its centroid is here. So if you just you balance it, this P force, so you balance here, so these are equal and opposite forces. So they are causing a counterclockwise movement, so there must be a clockwise moment applied at this location. Okay, so this is a clockwise moment. So these two forces are off at a eccentricity of 20 millimeter, because this hole is 40. So if it is applied at this centroid, so this must be 20. Okay, so now you have an axial force and a bending moment. This bending moment is negative bending moment. Okay, and this axial force is a positive. So Px is equal to P and m is equal to minus P into 20, so minus 20P. Assuming that if this P is in Newton, that this is in Newton millimeter. Okay, since 20 is in millimeter, so this the unit of this is in Newton millimeter. So I'm assuming that P is in Newton. Okay, P is in Newton. Now these are the forces acting on this cross section. Now the geometric properties, the cross section area is 50 into 40, and the moment of inertia is 50 into 40 cubed by 12. So this is the moment of inertia, and this is the cross section area of the member. Okay, now you have once again the combined stress formula. There is no my acting on this one, so there's I haven't written the my. So this is px over a plus or minus mz divided by iz into y. So P is plus P divided by 2000 minus, and this is minus 20P. So if you add them, so it will result in this value. Okay, so this is called the fiber stress equation. Okay, or the stress equation simple. Now for the neutral axis, if you just plug in this value, this equal to 0, so this will result in y equal to minus 6.67. So the neutral axis has shifted, in this case, downward. Neutral axis has shifted downward. Okay, Neutral axis has shifted downward. Now, the stress for the stress, since the problem is that the stress is limited to this one, so you will have to search the maximum stress. Okay, so you'll have to search the maximum stress. So in the top fiber, usually the maximum stresses are either in the top or in the bottom fiber. So in the top fiber, the value of phi is plus 20. So if you just simplify this one, so it will result 0.002 p. And in the bottom fibers, it results in minus 0.001 p. Okay, so this is 0.002 p and 0.001 p. Now the maximum stress is what? 0.002 p. Okay, now if you compare this maximum stress with strength of the material, which is 80 megapascal, and since our unit of deformation, displacement, or the linear unit are in millimeter and the force unit are in Newton, so this result in megapascal. Okay, so the unit of this is megapascal because Newton per square millimeter is a megapascal. Okay, so now comparing the stresses, so 0.002 p is equal to 80, so p is equal to 40,000 Newton or p is equal to 40 kilonewton. So the force which can be applied on this link without exceeding a stress of 80 megapascal at this location, and this location is basically what? The top fiber. This top fiber will have high stresses. Okay, so what will happen that if you apply a force of 40 kilonewtons, so the stresses will be within the limit of 80 megapascal. And if you are increasing the value of P beyond 40, so the stress will exceed 80 megapascal, and this will be a design failure. Design, what one is the structure failure? G.
सर इसमें बेंडिंग किस तरह पैदा होता है?
बेंडिंग किस तरह पैदा होता है?
ये होगा सर।
You have here you can see from this free body diagram, you have this force and you have this force, so these are equal and opposite forces, they are creating a couple. Okay, just like in the previous case. So this is also, if you just pull this up, so what will happen? It will move like this, it will bend like this. So this is since the forces cannot transfer like this, the force will transfer like this. This is the stress path. Okay, here it will pass like this, then coming here and then here, and it will pass like this. Okay, so this portion is under bending also, and this bending is due to this eccentricity. Okay.
Yes, sir.
Okay, this is a slightly difficult, but we'll have to carefully see what is happening in this problem. For the 2-inch by 6-inch wooden beam, here you can see 2-inch by 6-inch wooden beam. This is the cross section of this beam. Okay, this is 6 inches, so I've shown it like a exaggerated value. This is a large value of this. Determine the normal stress, and it is subjected to an inclined force of 15 kilonewton. So he's saying determine the normal stress at A and B. Are these the points of maximum normal stress? वो कहता है कि you calculate this and then comment if they are the maximum stresses. If not, then where is the location and what are these values? Okay, so you will have to then locate this one. Okay, so our first step is our first problem should be to calculate the stresses at A and B, and then we'll talk about the rest of the points. So to calculate stresses at A and B, we need the geometric properties. Since in this case, the cross section is subjected to, some of the cross section is subjected to an axial force and a bending moment about the z-axis. Here this is z-axis, so we need these properties, the cross section area and the moment of inertia about z-axis. 2 into 6 and 2 into 6 cubed by 12. Now at section AB, now let's talk about the solution of this to draw. This is the bending moment diagram and this is the axial force diagram. This is not the shear force diagram. Since the shear force diagram is not required, so I haven't drawn the shear force diagram. I've directly drawn the bending moment diagram. Okay. Now this is subjected to, let's talk about the analysis of this member. So this is subjected to an inclined force at this location, the location is 24 inches from this left support. Okay, this is the point of application of this inclined force, which is 2000 pound. 2000 pound. So now resolve this force, since this is an inclined force, resolve this force into its rectangular components. One is the horizontal component and the other one is vertical component. This is 2000 cos of 15, so it result in 1932, and this is 2000 sine of 15, which result in 518 pound. Okay, so these are now the two rectangular components of this. So now apply the equilibrium condition to calculate the support reaction. This is a hinge support and this is roller support. Okay, so if I apply a summation of fx, I'm doing it directly. I'm not using any kind of a calculation, and I'm not writing any calculation. Okay, I'm just using my calculator. I just calculated that this is the cos component, so this is the y component. I've written directly the values. Okay, so if you apply summation of horizontal force is equal to 0, so there must be a horizontal reaction here, and this force which is towards right will be balanced like a force towards the left, 1932. Okay, so now this whole system is balanced for horizontal forces. Okay, now to balance it for the vertical forces, let's take a moment about this left support, and suppose this reaction is R1 and this reaction is R2. R1 and R2, these are the reactions. Take a moment about this point. Okay, take a moment about this point about the left support. So R2 multiply by 36 plus 12 plus 24. So this is 72 is equal to, this is a counterclockwise moment, so it must be balanced by the clockwise moment. So 518 into how much? 24. This 518 times the 24, the moment arm is 24, minus there's this force also, 1932 into what? No, this should be, this is plus, because this is also clockwise and this is also clockwise. So 1932, the moment arm for this force is 3 inches. This total is 6 inches. So the distance from here up to the top, this is a force, the line of application of the force is 3 inches above this hinge support I have. Okay, so 1932. So this, if you just solve this problem, so it will result in what? It will result in 253 R1. If you just solve this one, so R2 will be equal to 253. Okay, 253. Now, if you just apply the summation of Fy, if you apply the summation of Fy to this case, sum of the vertical force is equal to 0. So R1 plus R2, R1 plus R2, now I know R2 is 253. R1 plus R2 must equal to 518. There is only one downward force. These are upward forces, and upward forces, equilibrium requirement is upward forces should be equal to the downward forces. So it will result in R1 equal to 256. Okay, so in this way I got all the reactions. I got all the reactions. Okay, all the reactions. Okay, so I have a horizontal reaction here and a vertical reaction here and a vertical reaction here. Now let's calculate bending moment. Okay. Okay, so just calculate bending moment at this location. So as per definition, bending moment, the definition of bending moment, that moment to the right or to the left of a section of all the sum of the moment of all the forces to the right or to the left of the section. Okay, so on the left of this section there is there are two forces. One is this force and this force. This force is not causing any movement at this location, but this force is causing a movement, and this force is causing a moment of 256 into 24. Okay, so 256 into 24 will result in 6360. Okay, so it will result in 6360. So here the bending moment is 0, and here the bending moment is what? 6360. Okay, so this is the bending moment diagram here. This is the bending moment diagram. Now if you just calculate the bending moment just to the right of this concentrated force, just to the right of this concentrated force, so you can use the right hand side. So 253 into 48, 253 into 48. So it will result in what? It will result in this one, 12144. Okay, 12144. And since this is a concentrated force, so I can join it like this one. So usually we do have, if we are calculating bending moment from the right or from the left, so we should get the same result. But since this section is what this section is, one section is to the right and other section is to the left, so they are not the same section. So if I'm taking this one, the force here, and calculating the moment from this one, from the right hand side, so I must have to include this horizontal and vertical forces. So vertical has no moment arm, but the horizontal force has a moment arm, so it will also result in 6360. So this is a kind of, if you want to, this is a kind of a concentrated movement. This 1932 is causing a concentrated movement at this location. So this is the bending moment diagram of this one. This whole is the bending moment diagram. So if I want to calculate, since at AB section the bending moment is required, the stresses are required, so the bending moment should also be calculated. So one thing is 253 into 36 will give you this one, or from the triangle proportionality. Triangle proportionality is what? 12144 divided by 48 into 36. This is triangle proportionality. Okay, so this will result what in 9108, or you can directly say 253 times 36. Okay, so it will also result in 9108 bending moment. Okay, so this is what, this is the bending moment diagram. Now come to the axial force diagram. Okay, so from here up to here there is an axial force. As you cross this concentrated force at this location, there is no axial force. Why? Because if you just see the right hand side, there is no axial reaction here. So there cannot be any axial force here. So from here up to here, there is only, if you just take a cross section here and take the the left hand side, so there must be a force here, the reaction, the axial force here, so 1932. So from here up to here, the section is subjected to an axial tension, and from this point beyond, there is no axial force or axial tension in this member. Okay, so this is the axial force diagram. So I've drawn the bending moment diagram, and I've drawn the axial force diagram. Okay, now these first calculate the geometric properties. So I've already told you that these are the geometric properties, this cross section area and the moment about z axis at section AB. This is section AB. What is the axial force? Equal to 0. There is no axial force. And what is the bending moment? 9108 pound-inch. This is the bending moment. Okay, so this is the formula. Sigma x is equal to this plus this. Oh, since this is 0, so this is the case of a pure bending. Pure bending, there is no axial force, so this is just a flexure formula, my by I. So this will give you sigma x is equal to minus 253y. This is the stress equation. So at top, sigma a is equal to 253 into 3 minus 759, and at the bottom minus 253 into minus 3. So you have plus and minus compressive stresses in the top fiber and tensile stresses in the bottom fiber, and they are of the same magnitude. Now you calculated determine stresses at A and B we have. Are these the points of maximum stress? Now you will have to comment on this. So I have written these stresses at section A, B are not the maximum because the moment under load is greater than the moment at A, B. ये क्यों जो है वो maximum नहीं है? ये इस वजह से कि कोई दूसरा point ये है. There is another point also. There is another point also. Just if you just under the load, so the bending moment is 12,144, which is higher than this one. Okay, which is higher than the bending moment under this. Just to the right of this, the bending moment is 12,144, which is higher than this one. So obviously the stresses will also be high. Okay, and there is another reason also that there is a possibility, not a solid reason. This is a solid reason that this is not a maximum value. But there is a possibility that if you just take a section just to the left, so just to the left, the bending moment is 6360, not 12,144. But there is also an axial force also. Okay, so there is also a possibility that it may result in a stress higher than this value. Okay, okay, so let's do calculation. What are these values? So at section just to the right of the point load, just here, just to the right. This is, I've shown it just a bit further, but this is very close to this concentrated load, a 0 distance apart. The axial force, there is no axial force. Just to the right, there is no axial force, and the bending moment is 12,144 pound-inch. Okay, so sigma x is px over a plus this, so this is 0, so you got minus 335 into y. So in the top you have minus 1011 psi, and in the bottom you have plus 1011 psi, and obviously they are higher than the previous values, okay, which are 759. So they are higher than this one. And let's investigate also this point. There is a possibility. So we need to investigate this point also just to the left of this section. Okay, so just to the left of this section, we have px is equal to, px is not now not equal to 0, 1932, but the moment is 6360, which is smaller than this one. So now this is a combined stress situation. So sigma x is equal to px over a plus minus mz by I z into y. Plugging the value, so you will get the fiber stress equation. So in the top fiber we have 370 psi, in the bottom fiber we have 692. So this is still less than this one. So the stress here is even less than the stress here. But the maximum stress is at the location 12,144. So therefore a maximum stress are at the section just to the right of point load. Point load okay, just right where the maximum stresses lies. Okay. Any question? Okay, so this is also another practical problem. You will also study the design of retaining structures. Okay, so dam is a retaining structure. It retains the pressure of water. Okay, so this is a retaining structure. So problem 911, a concrete dam has the profile shown in the figure. Profile means the cross section of the concrete dam. This is a trapezoidal cross section. At the top, this is 3 meter wide. At the bottom, it is 9 meter wide, and its height is 20 meter. Okay, 20 meter. If the density of the concrete is 2400 kilogram per cubic meter, and that of water is 1000 kilogram per cubic meter, these are the density of concrete and water. Determine the maximum stress on section MN. This is M, this is N, so section MN. If the depth of the water behind the dam is H equal to 15 meter, this is the depth of the water. Okay, so this is the water depth is not 20 meter, it is less than 20 meters, so this is 15 meter. Okay, so he's saying it calculate the stress is the maximum stress at section MN. Okay, so first just investigate what are the forces acting on this dam. There are three forces acting on this dam, or you can say two forces. One is the pressure and the other one is the weight of this dam. So these are two forces acting on this dam, pressure and weight of the dam. Pressure is trying to overturn this one, and weight of the dam is trying to stabilize this dam. Pressure is trying to slide this one, and weight of the dam is resulting in a friction force is trying to stabilize this dam. Okay, but he is not talking about the stability of this system. He is talking about the stresses. There is also a possibility when you apply a force, so higher stress is created at this toe. This M is known as a toe of the dam, and this is known as a heel of the dam. Okay, so this toe may result in very high stress, because when this force is applied to this one, so this is trying to produce a movement, and there is a possibility of high stresses at this M, and there is a possibility of tensile stresses at this end, because there may be an uplift when you just apply this force, so there is a possibility that this point N may uplift. Okay, so we want to investigate the stresses along this MN. So the force is acting, so we can divide this, the force acting on this dam, the weight of the dam, into two components. And let's suppose that the length of the dam is 1 meter, because usually dam is a very long structure. Okay, so we want to investigate just 1 meter. If we investigate 1 meter, the rest of the dam is same as this one. Okay, so 1 meter, the force acting on this 1 meter, the pressure acting on this 1 meter, and weight of this 1 meter. So we have taken this is the cross section at this base. So since this is 9 meter and we are taking 1 meter of this dam, so this is 1 meter by 9 meter cross section. Okay, now let's talk about this one. We divide this force into two. One is a rectangle, the other one is triangle. So the weight of the rectangular portion is W1 and the weight of the triangular portion is W2. So W1 is gamma into V. It's very easy. You just multiply the unit weight with the volume of the material. So the unit weight of this is 2400 is the density. So multiply this with 9.81. So it will give you the unit weight or the weight density. Okay, and multiply this with the volume. So the volume of this portion is 3 into 20 into 1. 3 into 20 into 1, or divided by 1000 just to convert this into kilonewton. So this results in 1412.6 kilonewton. Similarly, for this W2, gamma into V, so gamma is this one, and since this is triangle, so this is divided by 2. 6 into 20 divided by 2 into 1. So divided by 1000, so this is also resulting in 1412.6 kilonewton. And the force P, which is the pressure, so the pressure is the water pressure. You know that if this is H, then the pressure here at the bottom will be gamma H. And this, since this is a triangular variation, so the resultant force P will be equal to half of gamma H into H. Okay, half of gamma H square, this is what? This is P. Okay, half of gamma I square, and so also multiply the length of this. So length we have taken is the length of the dam is 1. Okay, so this is half into gamma, and the point of application is this is a triangular variation. So the point of application of this force will be at a distance of h by 3. Okay, h by 3. So since this is 15, so this p force will be acting at a distance of 5 meters from bottom of the dam. Okay, so we have gamma h square by 2. So gamma h square by 2 is equal to this 1000 into 9.8 into 15 square by 2 into 1. 1 is the length of this dam, so I haven't written this one. So 1103.6 kilonewton. Okay, so these are the forces acting on this time. Here you can see W1, here you can see W2. The point of application of the load are shown. This load W1 must be acting at the mid of this 3 meter, and this W2 must be acting at a distance of 1/3 from this. So this is totally 6 meters, so 1/3 is 2 meters, so it must be acting 2 meter. Okay, and now equilibrium, apply the equilibrium condition. So I'm applying just the 2 equilibrium conditions. The third one, I'm not applying summation of F in the horizontal direction is equal to 0 because it will result in a sliding force, and I'm not interested in the sliding force. Okay, sliding force will be equal to the speed. Okay, there will be a sliding resistance here equal to the speed. Okay, so px sum of the vertical forces, like this is the x direction and this is px, so px must be equal to w1 plus w2. Okay, px must be, but this will be negative because this px will be a compressive force. So 1412.6 plus 14.12.6, so 2825.2. So this is a compressive force here, and there will be a bending moment acting on this one. So bending moment, obviously when this force is applied, so it will cause a compression here, and this arrow must be towards the compression side. Okay, now this is always towards the compression side as per the sign convention of the bending moment. Okay, so my is equal to, my is this p, I've written this p into 5, this distance is 5, minus w into this distance, this is 1.5, and this is from this point and this point, the distance is 4.5, and this is 1.5. So 4.5 minus 1.5 is 3, so its moment arm is 3. W2 is on the other side, so it is plus, it is added with this p. Okay, this is 2 and this is 3, so 5, so 5 is toward this one. So the distance between these two is 0.5, so plus W2 into 0.5. So it will result in a bending moment of 1986.5 kilonewton. And now if you just look to this one, this is my, this is not mz. If you just, this is your my, then this bending moment is applied about the y-axis. Okay, about the y-axis. And this bending moment is a negative bending moment as per the sign convention. This is a negative moment. If you press your finger, on the compression phase, M is the compression phase of this one. Okay, if you press your finger on the compression phase, your thumb will be in the direction of the moment vector. Okay, if you press the finger of your right hand on the compression phase, your thumb must point the moment direction. So we know that compression phase. Okay, so my thumb is pointing in this direction. Okay, so compression phase, my thumb is pointing in this direction, and this is a negative moment. So this section, this MN section, is subjected to an axial compressive force and a negative bending moment about y-axis. Now, this is a combined stress formula. So just calculate the geometric properties. So the cross section of this is 9 into 1. And the moment of inertia about y-axis, I need the moment of inertia about y-axis. So 1 into 9 cubed by 12, so 60.75. Okay. Plug in the formula. Now you can see there is no negative sign here. So plug in the formula. So px divided by 9 and my divided by iy into 3. So this is the stress formula. Again, this is the stress formula. Okay, or the fiber stress formula, which is given you the stresses along at any point along the z-axis. Okay. Now at point M, what will be the value of z? The value of z will be plus 4.5. Plus 4.5, so it will result in 461 kPa. And at point number N, the value will be minus 4.5, so it will result in minus 166.82 kPa. So there are high stresses at this location and lesser stresses at this location. If I draw the stress variation diagram, let me pick another color. So here the stress is high, here the stress is low. This is the stress variation line. This value is 461, value is 167, negative and negative. Okay. So this is the stress variation diagram. The whole section is under compression. The whole section is under compression. Now, if there's a possibility, if you increase this pressure, then there is a possibility that there could be a stress, a tensile stress at this location. If you do have a tensile stress, since there is no contact between the soil, there is a soil beneath this one, so there is no contact between them. At the contact, there couldn't be any tensile stresses. So what will happen? It will lift, and when it lifts, so there will be seepage of water, and which will cause in underground tunneling, and which will result in complete failure of this dam. Okay, so tension is not desirable, and we'll talk about this, the non-desirable nature of this tension in the case of coming lecture. Okay. So, short prismatic members. This is another topic of the combined stress. Okay, short prismatic member. Short. The word short means that there is no chance of buckling. We'll talk about the column in our in our course after the midterm. Okay, in which we will study the long member. Okay, the long member, but here short mean that there is no buckling chance. The cross section is such that it is not susceptible to the buckling. Then prismatic mean the constant cross section member. The cross section of the member does not change along the length of the member. Okay, so short prismatic member with known principal axis. Now you know the principal axis, an axis about which the product of inertia is zero. So the axis of symmetry are the principal axis. So if the principal axes are known in advance to you, then we are first talking about that case that if you know the principal axis of the section. So here you can see the cross section which is subjected to an eccentric force, not a concentric force. Concentric is very easy, of px over a. If you have applied a load applied at the centroid of the cross section, then the stress result will be just p over a. So this is a concentric force applied, eccentricity. These are known as eccentricities. Okay, the eccentricity along z-axis is what Ez, and along y-axis the eccentricity is Ey. And y and z, this y and z are the principal axis. This is the centroid. Okay, and y and z are the principal axis, and that is about these axes the product of inertia is zero. Okay, and I've already talked about this Ey, Ez. They are defining the position of load. Okay, A, Iy, Iz are the geometric properties, the cross section area, the moment of inertia about y, and the moment of inertia about z. Okay, the eccentric load P may be shifted to the centroid of the section, accompanying by a moment about y and z axis. You can shift this force to the centroid. Here you can see when you just shift this force from this location to the centroid, it result in what? It result in two movements. One is the movement about y-axis, and another one is the movement about z-axis, about the negative z-axis. Okay, so this is PEZ, and this is PEY. So how we got this movement? Okay, and you also know this from your engineering mechanics, and if you want to shift a force from one location to another location, it must be accompanied by a bending moment. Okay, it must be accompanied by bending moment. So how we got these two moments? So let's talk about this one in this figure. Okay, this is a step-by-step procedure how you transfer load from this location to the centroid. So first, this is a force applied at this location. So I'm applying two forces above and below at this location. Let in the cross section, I'm applying the force at these are the cross section of the same figure. So the force is applied this here you can see the circle P. So the force is applied here. So I'm applying two equal and opposite forces here. Okay, so this one and this one are two forces. So since one is a tensile force, the other one is a compressive force, so there is no effect on the body, or the effect produced by the tensile force will be cancelled by the effect produced by the compressive force. So this is still in equilibrium, and there is no effect on the body of these two forces. Okay, now if you just look to these two forces, they are equal and opposite forces, and they are creating a couple, and the couple is PEZ. They are PEZ distance apart, and they are creating couple about the y-axis. They are creating a couple about the y-axis. This is the y-axis. This is y-axis. So the distance between them is EZ. So P into EZ is creating a moment about y-axis. So replace these two forces with a moment PEZ, and you have now you shifted force from this location to this location, but it is accompanied by a moment PEZ about the positive y-axis. Now you have now this case. Now apply two equal and opposite forces at the centroid of the cross section. Okay, two equal and opposite forces. So this is same as this one, no difference in these two. Okay, now once again these two forces, this force and this force, these two forces, they are creating a couple. They are EY distance apart, so they are creating a couple P is Y. Okay, they are creating a couple PEY, and this couple is about z-axis. This is what this is about, z-axis, and just this direction is according to the right hand rule. If you just see and rotate your finger in the direction of this couple, so your thumb will be pointing along the negative z direction. Okay, negative z direction. So this is creating a moment about the negative z direction PEY. Okay, now you just convert this eccentric force into a concentric force, but that is accompanied by these three forces. Here you can also see the same procedure in a two-dimensional view. Okay, in a two-dimensional view in a cross section. So here you can see that you now have here you have a eccentric force. Now you have a concentric force and two bending moment. Okay, two bending moment, one about the z-axis and one about the y-axis. Okay, so you can shift a force from one location to the other location. So in this case, I have shifted the eccentric force to a concentric force. Okay, now let's do formulation for this case. Now I have this case and I've shifted this one. So there is an axial force Px equal to P. There is a bending moment about y-axis, which is about the positive y-axis. So bending moment about the z-axis, which is mz equal to minus PEY. Minus is because this is about the negative axis. Okay, so now I have a combined stress case. When there is an eccentric force applied, so this is a combined stress case. So the combined stress formula, sigma x is equal to Px over A plus minus mz divided by z into y plus my divided by z into z. So So just plug in the value, these values. So P, replace Px with P plus My with this one and Mz with this one. So this is Mz and this is My. Okay, and so finally I'll get this one. So all the negative signs are now balanced, and this is all the signs are now positive. So P over A plus P into Ey divided by Iz into Y plus to Ez divided by Iy into Z. Okay, so this results in what? This result in stress. This is the equation which is giving you stresses at any point within this member. When you apply a force, so you want to calculate stresses will be produced. So this equation will give you stress at any point. If you just look to this one, this is the equation of a plane. This is equation of a plane. We'll talk about this one. There is a problem. So when we just study the problem, so you will see that you will get a plane of stresses. Okay, so this is not a fiber stress equation. This is a stress equation, but this will give you a plane. Okay, a plane. This is the equation of a plane, that the stress created will be like a plane. Okay. Now we can write this equation. This is the stress equation which is applicable to this prismatic member. So we can write this equation in another form also. For that, we'll be using this expression that Iz is equal to ARZ square. And I think the section, कौन सा था section? Section U. Or E. Section E was not familiar with this one. With this radius of gyration, what about you? Have you heard the word RZ or RY, the radius of gyration?
No, sir.
No, sir.
No. Okay. So we can write the moment of inertia in this format also. And by definition, the radius of gyration is like R is equal to I by A under the root. This is the definition of the radius of gyration. You can calculate the radius of gyration using this formula. For rectangular section, this is I we know is equal to BH by 12, BH cube by 12, and the area is BH under the root. So B will cancel with B1, H will cancel with H, so H square will remain. So H divided by under root 12, which is 2 under root 3. So this is the radius of gyration of a rectangular section. It's just a linear number. This is the radius of gyration of a rectangular section. Now, what is the physical interpretation of this radius of gyration? So we have a rectangular section in one case. Okay, this is, let's suppose, a z-axis, and if we just locate the same area, this is area A, and if we locate the same area A as a strip at a distance of r, which is the radius of gyration from the same z-axis, then both of them will result in the same moment of inertia. Okay, if you just arrange this, so this is the physical interpretation of this one. So this is a strip area, so strip A. Okay, the area of this strip is same as this one, but this dimension is very small, negligible, and it's like a strip, a long strip, and it is placed at a distance of r. The strip is placed at a distance of r from this desired axis. So this will result in the same moment of inertia. Okay, the moment of inertia of this is same as the moment of inertia of this rectangular section. Okay,
So this is the physical interpretation. We also know that the formula that if you want to calculate moment of inertia about any axis, so you calculate the moment of inertia of the about the centroid plus AD square. This is the shift formula. So if you apply the same case to this one, to this case, this formula, since this is a strip and whose vertical dimension is approaching 0, so BH cube by 12, so H is almost 0 as a very small number. Okay, for this BH cube by 12 is almost equal to 0. Okay, because this H is very small. Okay, so for this, the moment of inertia about its own axis is 0, and there is only AD square. So AD is the distance between the centroid of this one and the distance of the desired axis between desired axis. So since this is R, so here I will be equal to I will be equal to 0 plus A, and D here is R, AR square. So AR square, I is equal to AR square. So this is what this is, the same equation. Okay, so the moment of inertia, you can write in the moment of inertia in this form also. Okay, in this format also, that you can write the moment of inertia where R is the radius of gyration, and this is just a mathematical number. It has no physical यहाँ से लेकर यहाँ तक distance you have from the distance from this point up to this point will be like a physically this one. This is not like this one. This is a number. Okay, just like the moment of inertia, just like the cross section area. So this is also this radius of gyration is a number and whose magnitude can be calculated by I by A under the root. Okay. So you can write the moment of inertia in this format also. Iz is equal to ARZ square and Iy is equal to ARY square. So if you plug in Iz and replace Iz and Iy using these, so you will get this one. So now you can take P over A common. So this is the formula. Okay, 1 plus Ey divided by Rz square into Y plus Ez divided by Ry square into Z. So this is what this is similar formula to this one. Okay, both will result in the same thing, but they have some different application. In this formula, remember one thing, that Ey and Ez, they are referring to the position of load because they are eccentricity, they are defining the position of load. And Y and Z are defining the position of stress, where you want to calculate the stress. The load may be placed here, but you may need to calculate stresses at this location, stresses at this location, stresses at this location, stresses at this location, stresses at this location. So the Ey and Ez may have a fixed value, but you can calculate stresses at any other location, at any location, so you can have some different values of I and Z. So Ey and Ez are also variable in this equation. They are defining the position of load, and Y and Z are also variable. They are defining the position of stress. So this is important. Okay, and same is this case also in this formula. Neutral axis. In the case of a short prismatic member, how to define a neutral axis? So we have this formula. And for neutral axis, stress is equal to 0. If you plug in this equal to 0, so you will get this equal to 0. And if you rearrange this formula, just bring this 1 to this side, minus 1, and then just minus this 1, and then keep it minus minus. And then write it in this format. So Y divided by Rz square minus Rz square by Ey and minus Ry square by Ez. Okay, so these are what these are for a particular Rz and Ry are the cross-sectional constant, and Ey and Ez are the position of load. So if the position of load is known to you, then you can plug in this value, so it will result in a number. It will result in a number, a positive or a negative number. Okay, and this form of the equation, so this is a number. Let's replace it with Cy and this with Cz. Okay, Cy and Cz. So these are what this is known as the intercept form of the equation. This is the y-intercept and this is the z-intercept. Okay, and here you can see this is z-intercept and this is y-intercept. So these intercepts you can calculate using this equation. Okay, using this is one intercept and this is another intercept. Okay, so this do not depend on the magnitude of the load. Okay, this depends on the on the eccentricity. Okay, so position of neutral axis depends on the eccentricity, not on the magnitude of the load. Okay, so this will give you, thus if you just plot this eccentricity and then join them, this will give you the neutral axis. So now the neutral axis had shifted and rotated. Neutral axis shift bhi hua hai or rotate bhi hua hai. Okay, the neutral axis has shifted and both rotated. Since if you have a case, if you have bending moment about both the axes, just like this case, so in this case the neutral axis will rotate also. ठीक है ना, वो rotate भी होगा और shift भी होगा. Now this is a problem. Okay, this will clear this whole formulation and all these things. So for the given short parametric member, locate the neutral axis and calculate stress at point A and B. Take P equal to 100 kilonewton. This is a rectangular section. This is a prismatic member having a T section subjected to an eccentric load. This is not applied. This is the centroid, so the load is not applied at the centroid at this point, and its magnitude is 100 kilonewton. Now, in this case, the load is applied here, but we don't know the eccentricity because we don't know the centroid of this cross section. So first we'll have to look at the centroid of the cross section. We know the y-axis, the y-centroidal axis, but we don't know the position of this z, because this is the axis of symmetry, so this is known to us. Every axis of symmetry is a centroidal axis. In fact, that is a principal axis. Principal axis v, centroidal axis z hota hai. So, but you will have to locate this z-axis. So now we have the cross-section area. If we divide this into two rectangles, one in 10 into 60, the other one 50 into 10. So 1100 square millimeter is the cross-section area. Y bar is equal to summation of AY divided by summation of A. So if this is my reference, this bottom is my reference, then 600 is the area of this one. So 600 into 30. Plus 500 is the area of this, 500 into 6 plus 5, 60 plus 5 is 65. Divided by this one, so 45.9. So the neutral axis lies, centroidal axis lies at a distance of 45.9 millimeter from bottom of the section. Okay. Now also calculate the moment of inertia about the centroidal axis, about z-axis, about y-axis. So Iz is equal to, this is the formula. So this is equal to 10 into 60 cube for this rectangle, 10 into 60 cube by 12 about its own centroid, plus area into d square. So d is what? D is the distance between the composite, centroidal axis and the centroidal axis of the individual area. In this case, the centroidal axis of the individual area is this one. This is the centroidal axis, the centroid of the individual area. So this distance is how much? This distance is 49.5 G. Any question? कोई मसला है?
हेलो सर.
जी जी, कोई मसला है?
यस सर. सर आपने वो जो वही बार में 600 मल्टीप्लाई टू 30 किया है सर. 30 किस तरह?
ये आप अगर इसको देख लेना, मैं यहाँ से if this is 600 इसका एरिया है.
यस सर.
और ये डिस्टेंस इसका जो सेंट्राइड है वो बेस से मैंने ये रेफरेंस लिया है. सो यहाँ से इसका सेंट्राइड 30 पे आ रहा है. 60 डिवाइडेड बाय 2 इज 30.
यस सर. थैंक यू. ठीक है.
ओके जी. अच्छा, सो 10 into 60 cube by 12, 10 into 60 cube by 12 plus 600 into 49.5. ये जो डिस्टेंस मैं कह रहा हूँ, दिस डिस्टेंस is 45.9 minus 30. This distance is 30. This is 45.9. So this distance is 30. So what is the shift distance? You want to shift moment of inertia from this point to this point. So the shift distance is this one. And this is what 45.9 minus 30 square. Similarly, for this case, 50 into 10 cube divided by 12 plus 500 into this distance, the centroid here is, this is the centroid, and I need this distance. I'm sorry. Yahan tak. Yeah, distance. Okay. So since the distance up to this point is 65 and the distance up to this point is 45.9, so 65 minus 45.9 square, so it will result in this value. Okay. Now the moment of inertia about y-axis. This is the centroid. One rectangle, and this is the centroid of another rectangle. Okay, and both the centroid lies on the centroidal axis of the composite section. If you just look to this one, the centroid of this is lying on this and the composite section. The composite section centroid is this y bar, and this is also lying on the same, okay, on the same centroidal axis. So there should be no shift term in this case. So you need just to calculate BH cube, yani 60 into 10 cube by 12 for this one, and 10 into 50 cube by 12 of this one. The shift terms are 0 because there is no distance. The z is equal to 0. So this is 109,167 millimeter. So now we know the centroid and we know the geometric properties. So now the eccentricity of the load, now the eccentricities are with respect to the centroid, okay, centroid of the composite section. So if load is P here, so its EY is this one. This is 24.1 minus 10 is 14.1. So this is plus 14.1 up here, so this is 14.1. Okay, and the distance from here up to here is 25 by 2, but negative. This is on the negative side, so minus 25. Okay, so now we know the eccentricity of the load and we know the geometric properties. Now first, we want to write the stress equation. So the stress equation, the equation of plane is sigma x is equal to P over A plus P EY into IZY plus P into EZ divided by IY into Z. So just plug in P is equal to minus, P is a compressor force, so minus 100,000. Minus 100,000 into 14.1 divided by the moment of inertia, and minus 100,000 into 25, the eccentricity divided by this. So if you simplify this one, so sigma x is equal to minus 90.91 minus 2.721 y or plus 22.900 z. So this is the stress equation. This is the stress equation, and if you just look to this one, so this is the equation of plane. You have two variables. Okay, this is the equation of plane. Okay, now from this equation of plane you can get the equation of the neutral axis. The neutral axis, if you just plug in this sigma x equal to 0 in this equation, and if you simplify this one, so this is the equation of the neutral axis. Okay, this is the equation of the neutral axis. You can write this equation in this form also. Okay, y divided by, just simplify this one, and like y divided by 2.721 divided by 91 will result in this value. And y divided by 90.91 divided by 2.72, so 33.4, and this will be equal to 90.91 divided by 22.9, so this will result in 4. So this is the intercept form of the equation. intercept form of the equation. So I have y-intercept as minus 33.4. So if I have this come down and this is minus 33.4, so this point, and z is plus 4, so just move on the positive side, so plus 4, just close to this line, so plus 4. So if you join this point with this point and draw a line, so this is the neutral axis. So the neutral axis had shifted and the neutral axis has rotated. ठीक है ना, वो shift भी हुआ है और वो rotate भी हुआ है. Okay, so shifted and rotated. So this is the neutral axis. So on one side of this neutral axis there will be positive stress, on the other side of the neutral axis there will be negative stress. Since the load is applied here and the load is compressor, so on this side there will be compressive stresses and on this side there will be tensile stress, and we will see this. Okay, so the question is saying that calculate the stresses at point A and B. So just in this equation you will have to plug in the coordinates of A and B. So stress at A minus 90.91, minus 2.72, and what is the y coordinate of this A is plus 14.1, and what is the z coordinate of A is plus 25. So just plug in plus 14.1 and plus 25, so you will get 443.2. This is a positive value and it should be, because this is on this side, so at A there should be a positive stress. Okay, sigma B, B पर भी positive होना चाहिए क्योंकि ये भी इसी साइड पर है, and the coordinates of B are minus 45.9 for Y and plus 5 for Z, plus 5, because this is on the plus Z side. Okay, so if you plug in the value, you will get plus 148.5 MPa. So you are getting plus 48.5 MPa stresses. Okay, tensile stresses at both A and B. Now in the coming slide, this is now over. This is let me read the statement that he is saying locate the neutral axis. So we located the neutral axis and calculate stresses at point A and B. So we calculated. So this is now the problem is over. But I am not ending it here. I am just extended this example and I am calculating the stresses at all the points, all the corner of this T section. सारे टी सेक्शन के कॉर्नर पर जो है वो मैं इसके स्ट्रेसेस कैलकुलेट करना चाहता हूं. ओके, स्टार्टिंग फ्रॉम दिस पॉइंट, दिस इज माय पॉइंट 1, दिस इज पॉइंट 2, दिस इज द पॉइंट वेयर द लोड इज अप्लाइड, दिस इज पॉइंट 3, दिस इज पॉइंट 4, पॉइंट 5, पॉइंट 6, पॉइंट 7, पॉइंट 8. सो देयर आर 8 पॉइंट्स. ओके, so these are the coordinate for point number 1, 24.1 and minus 25. For 2, 14.1 minus 25, and these are the coordinate accordingly. When I plug in this formula, this is the formula. When I plug in the value in this formula, so I got these stresses: minus 729, minus 701, minus 243, minus 80, plus 148, minus 14, plus 443, and plus 416. I just plug in. So I've represented these values in a table, so that there are many values, so they are easy to understand. So just plot these values now. Plot these values. This blue color, light blue color, is the cross section. Okay, this is the cross section. Now, this is the stress 729. This is slightly less than this one, 702. This is 244. So I'm joining the line 244. And here this is 80, I'm joining, so all of them are having negative stresses. Okay, all of them are having negative stresses. Now when I calculated the stress at B, so I got a positive value. When I calculate stress at this point, okay, this point is point number what? This is point number 6. Okay, so I got a negative value. If I'm moving towards the previous slide, and if you just look to this one, so this point is slightly towards the right. This point is slightly towards the right of neutral axis, and at the right of neutral axis there are compressive stresses. Okay, there are compressive stresses. So I'm getting a compressive stress here. Okay, point number 6, and similarly point number A. The stress is point A is actually the 7 number point. So this is 443. and this is 416. So the maximum compressive stresses are at this point, and the maximum tensile stresses are at this point, 443. Okay, so here you can see, just if you look to this purple color or this pink color, so this pink color is a plane, like if you join all the lines and it will result in a plane. Okay, this is a plane, like this is same. If you just rotate this T section, and you will get this plane. Okay, this is a complete plane. Okay, you rotated this T section and you got about this neutral axis. You rotate this T section about the neutral axis, so you will get this stress field. Okay, this kind of a stress field. So this is the equation. This is a plane, and this is the equation of a plane. Okay, so this is how to get stresses and how to calculate, how to locate the neutral axis. Okay, uh, we'll talk about this the coming after a break. Okay, so just take a break of 15 minutes. If you have any question, you can ask the question. Otherwise, we'll due for a 15 or 20-minute break. I'm sorry, 20-minute break.
अच्छा जी, अस्सलाम वालेकुम। शुरू करते हैं जी। आवाज आ रही है मेरी?
यस सर।
ओके जी, चलो। अच्छा, हमारी डिस्कशन जो है वो उस पे जो है वो शॉर्ट प्रिज्मेटिक मेंबर पे हो रही है, जिसमें प्रिंसिपल एक्सिस जो है वो नोन है, ठीक है ना। अब इसकी एक और जो है वो इसी से रिलेटेड एक टॉपिक है, कर्न ऑफ ए सेक्शन। कर्न ऑफ ए सेक्शन को समझने के लिए जो है वो पहले इस सिचुएशन को जरा जो है वो समझे, ठीक है। ये दिस इज नॉट द क्रॉस सेक्शन, दिस इज द फ्रंट व्यू ऑफ ए मेंबर। क्रॉस सेक्शन इसका जो भी है, ठीक है ना, वो क्रॉस सेक्शन, लेट्स सपोज इट्स क्रॉस सेक्शन इज assumed to be rectangular, या कोई और जो है वो इसका क्रॉस सेक्शन है। जब लोड जो है वो, when the load is applied at a certain location, ठीक है, at the centroid, so the stress produced will be uniform, ठीक है ना। जब एक प्रिज्मेटिक मेंबर पर जब सेंट्रॉइड, when the load is applied at the centroid of a prismatic member, the stress field will be uniform, okay, and this we know that the stress will be equal to P over A. When you start to move load away from the centroid, the stresses on the side of the load will get increase in compression, and the stresses on the opposite side will get decrease in compression. And if you further move, a stage will come when the stresses on this side will become zero, and then stresses on this side will become a higher value. Okay. Now, if you further move the stress, the load away from the centroidal position, what will happen? Tensile stresses will produce in the member. Okay, just like you can see, there are some tensile for stresses. This is the neutral axis, and there are tensile stresses in the member. Now, in some structures like dams, retaining structures, tension is not desirable. We don't want to have any tension in the member. Okay, we don't want to have any tension in the member. We don't want this kind of a situation, because since the contact is not a restrained contact, this is just you just put a concrete wall on the soil, or you just place the retaining structure on the soil. So there is no physical contact between the two, and there just one is placed above the other. So the contact pressure can develop, but the tensile stresses cannot develop. And what will happen if there is any tension develop? So it will lift. The tension cannot develop, so tension is not desirable. Or there is a possibility that the material may be very weak in tension. Okay, so it has a very less resistance against the tension, and it is not desirable to develop any kind of a tension. Okay, as it may result in the case of a dam, it may result in some problems, which is a seepage or failure of the structure. Okay, so we want to keep load at a certain limit around the centroid. If the load is at the centroid, so okay, there's no tension, uniform stresses. So we don't want to move the load away from this position. We want to keep it near the centroid. So this is the final position where the stress at this is zero. If we further move it, then there is a chance of tension. So we don't want, we want to limit this. So limiting this, so there is a region, this is the centroid, and there is a region around the centroid. And if you want to place a load within that region, there will be no tension in the member, in the cross section. Okay, there will be no tension in the cross section. So here I can you can visualize these things in a three-dimensional view. So this is a cross section, and this is a region. If you want to place load within this region, the whole cross section will be under compression, and there will be no tension. And if you want to place a load outside this region, and this region is known as the kern of this section. If you want to place a load outside this region, what will happen? A part of this section will be under tension, okay, which is not desirable. So we want to keep it. So the definition of the kern region is important. the determination of the cone region is important. You should know this is the cone region, and you want to place the load within that region, the resultant of load within that region. Okay, so thus there is a region surrounding the centroid of a section such that any compressive load applied in this region will result in compression in the whole section. Okay, this is a region where the load is applied. Okay, remember where the load is applied, and you want to see the stresses in anywhere in the section, and if the stress is not zero, is not tension, then this region is a cone. Okay, the load is placed within the cone, and if you are getting some tension, then the load is outside the cone. When the load is applied at the boundary of the cone, at least one point will be under zero stress. If you are applying at the boundary, like if you are applying a load here, so there is a possibility that there will be a point somewhere here that the stress will be zero. Okay, let's suppose this is the cross section of the member. So if you are applying a load at the boundary of the cone here, then there is a possibility that the stress at this point will be equal to zero. When the load is applied outside the cone, a part of the section will be under tension. If you are applying a load here, then probably this part will be under tension. There will be a part which will be under tension. So now to formulate this thing, so to get a formula for the cone of a section, to locate the cone of a section, let's do some formulation. So consider a prismatic member as shown. A load P is applied at the boundary of the cone. Let's assume that this load P is applied at boundary of the cone, and the eccentricity of the load are EY and EZ. Okay, and let the stress at point Q is zero when you apply the load. So there is a point, there should be a point where the stress is equal to zero. So let's suppose that point is Q. So the stress at Q is equal to this one. This is the short prismatic formula. When if you plug in this equal to zero, so you will get this one. Okay, the stress at this point is equal to zero. Okay, so this is the case. So EY divided by RZ square into Y, EZ divided by RY square into Z is equal to zero. And in this case, Y and Z are known. The point is known where the stress is zero. Okay, we want to get an expression of EY and EZ. So here these are unknown and Y and Z are known. So this is the equation of cone. You can write this equation in this format. Okay, just like we wrote the expression, the equation for the neutral axis, and this neutral axis we put this Y and Z here and EY and EZ here. But here the unknown are EY and EZ because we want to locate the boundary of cone. The point is known to you. So this is the equation. So this is EY divided by CY plus EY divided by EZ by CZ is equal to 1. So this is the equation of cone. So you need just to know the CY and CZ value, and this is the line equation. And this line will become not the whole line, but a part of the line will become a part of the cone of a section. And we'll discuss this in an example. This is the equation of line representing position of load resulting in zero stress. Okay, this line may be part of the cone of a section. This is a line like there is a line here. Let me draw that line. So let's suppose this is that line. Okay, and this point is on this line. So this line, if you place load here, anywhere on this line, the stress at Q will be equal to zero. Okay. And if you move the load towards this one, so compressive stresses will be developed at this point. If you move the load away from this, then tensile stresses will be developed at this point. So it means that your cone should lie towards the right. Okay, because tension is not desirable. You cannot move the load to this side. You can move load to this side. So the cone is towards the right. Similarly, if you get a number of lines, okay, you get a line here, 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 and this area enclosed by these a number of lines, so that will be cone of this section. Okay, so you should have enough points just to cover the whole thing, the whole cross section. Okay, so thus the cone of a section is obtained by selecting various Q points. Okay, just like you take this Q point, this Q point, this Q point, this Q point, just making at the boundary, just selecting a number of points, and you will get a number of lines and draw those lines.
Okay, and finally that will give you the area enclosed by those lines will be kern of this section. The region surrounded by these lines will be kern of their section. Okay, so let's talk about the kern of rectangular section. Okay, kern of rectangular section. Kern of rectangular section may be, this is the rectangular section B and H. So kern of rectangular section may be obtained by making stress equal to 0 at each corner one by one and obtaining equation of lines 1, 2, 3, 4 representing boundary of kern. You get stress, take stress equal to 0 at point number 1, so you will get line number 1. Then you make stress equal to 0 at point number 2, you will get line number 2. Then make stress equal to 3 equal to 0, you will get line number 3. Similarly, take stress equal to 0 at 4, you will get line number 4. So take just the same stress equation, just like this equation. Okay, this equation, and then making stress equal to at 1 equal to 0, at point number 2 equal to 0, at point number 3 and point number 4, and you will get a number of equations. So just doing it like this, so it's better just to get the intercept of the line. Okay, so I have done it using this expression, this tabulated form. Okay, this for rectangular section, the radius of gyration square is IZ by A, which is equal to H square by 12. This is the square of the radius of gyration. Okay, and about this is R square and RY square is B square by 12. Why this is double A. Okay. Okay, so these are the radius of gyration, and we know CY CZ. Okay, so this is the value of CY. So for point number 1, the value of Z is B by 2 and Y is H by 2. So Z is B by 2 and Y is H by 2. So, and RZ is H square by 12. So plugging in this expression, H square by 12 divided by Y, which is H by 2. So you will get what? You will get the value of CY, which is H by 6. And if you plug in this expression, the CZ value is RY square, which is B square by 12 divided by Z. Z is how much? Z is B by 2. So it will result in minus H by 2. So minus B by 2 minus H by 2. These are the intercepts. Okay, so minus B by 2 is this one, and minus H by 2 is this one. This point and this point. Just join these two, so this will, you will get this line. So this is point number 1. Okay, so this point number 1, if you place load here, 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 anywhere on this line, the stress at 1 will be equal to 0. Okay, the stress at 1 will be equal to 0. Okay, and if you place the load on this side of the line, then the stress at 1 will be tension. And if you place the load on this side of the line, then the stress at 1 will be compression. So this line number 1 is showing that the kern is lying on this side. Okay, the kern is lying on this side of this line. Okay, similarly for point number 2, these are the coordinate. If you plug in this value in this expression, so you will get CZ and CY, so P by 6 and H by 6 for point number 2. Okay, minus plus B by 6 and minus H by 6. Okay, so if you just join these two one, you will get this point number, line number 2. So the kern is on this side of this line. Similarly, get for point number 3, get this line and this line. So this is the area enclosed by these lines, these 4 lines is kern of this section. Okay, the area enclosed by this line is kern of this section. Okay, this is a diamond shape. Okay, so this is B by 6, so this whole is B by 3, this is B by H by 6, this whole is H by 3. So the kern of section is in the middle third portion, and it is of a rectangular portion. So if you are placing the load within this kern, so don't worry about any tension. So there will be no tension of any magnitude. The magnitude of load is not, this is a geometric property. Kern is not a load property. This is a geometric property. Any magnitude load you apply, a compressor load. Okay, so there will be no tension. If you apply at the boundary, so let's suppose if you apply at this point, can you see the pointer? So this point, if you apply the load at this point, pointer nazar razi? Okay. So if you apply the force at this point, then the stress at this 4, 3 line at this point number 4, because this point lies at equation at line number 4 and line number 3. So the stress at this will be 0, the stress at this will be 0. In fact, the stress on this whole line will be equal to 0. Okay. So this point, when you apply a load on this point, so the stress at this point will be equal to 0. And when you apply the stress outside this section, then a part of the section will be under tension. Okay, and there will be some neutral axis, but in this case, the neutral axis, if you are applying the load, so the neutral axis will not fall within the cross section. There will be not actual neutral axis because the whole cross section is under compression. So this is the way how to get the centroid of a rectangle, the kern of a rectangular section. Right? You will have to take the stresses at this point equal to 0 and get the equation, write the equation in an intercept form. So and plot those lines, then you will get this kind of a thing. Okay. So I've done it in a tabulated form. Okay. मैंने tabulated form में इसको जो है वो कर दिया. Now let's talk about a kern of a T section. Okay, kern of a T section. This is the same T we discussed earlier. Okay, so I'm not talking about the geometric properties of this T section. This is that same T section 45, which the centroidal axis is 45.9 from bottom and 24.1 from top. And this is the geometric property. A is equal to this one, I, Z, I, Y. These are the geometric properties. Let's calculate the radius of gyration square. Okay, so the radius of gyration square is 471 millimeter square and Ry is 99.2 millimeter square. And these are the Cz and the Cy equations. Okay, you have the Rz and the Ry expression. You know these things. Okay, so now this is the formula. Okay, you can have it is equal to Cz is equal to Ry square, so minus 4 minus 99.2 divided by Z. This is equal to minus 471.1. Okay, so this I've written the formula. I've just plugged in the value since I've calculated the value of Rz square and Ry square. So this is Ry square minus Ry square by Z. Okay, so you have point. This is a symmetrical section. Okay, this is a symmetrical section. So I'm taking point number 1, point number 2, point number 3, point number 4 only, and the rest I will do by the symmetry. Point number 1, for point number 1, I'm making the stress at point number 1 equal to 0. So at point number 1, for point number 1, this is point number 1, the z coordinates is plus 25 and the y coordinates is 24.1. So if you plug in this expression, 99.2 minus 99.2 divided by z and 25, so it will get minus 4. And similarly, minus 471.1 divided by 24.1, it will result in minus 19.5. Okay. So these are the two intercepts. Similarly, for point number 2, for point number 3, point number 4, I got the intercepts. Okay. So I'll plot these intercepts. Just look to this point, line number 1. Okay. Its first intercept is minus 4 somewhere here. Okay. The z-intercept, and the y-intercept is minus 19.5 somewhere here. This is minus 19.5. Join these two lines. Okay, this is 1 and 2. They join this one, so this you will get this line number 1. Okay, then for 2, minus 4 and minus 33. Okay, line number 1. Okay, and line number 2, this is minus 4 is the same, and this is 33. Minus 33.4. So just join this one, so you will get this second line. Okay, you will get this second line. Okay, next is what? Next is point number 3. Point number 3, the intercept are minus 19.8, this one, and minus 33.4, this one. So you will get this line. For line number 3, and line number 4 is in minus 19.8 and plus 10.3. They get plus 10.3 this point. So just join them, so you will get this line number 4. Okay, so let me zoom it. Okay, so this is the situation. This is line number 1. Okay, and this is line number 2. Line number 2. So a part of this is, if you just enclose this small portion from here up to here, they are intersecting at each other somewhere here. These two lines are intersecting each other somewhere here. So the area enclosed by this one is, I'm taking this up to this intersection, then up to this, the intersection of this line, and then from here up to here, the intersection of these two, this line. So I got this half portion. So if I mirror it, okay, so I'll get the next half portion. So the next half portion will also be like this one. So this is what, this is the cone of this T section. Okay, this is cone of this T section. If you want to place the load, if you don't want to get any kind of any kind of tensile stresses in this case, then just place the load inside this cone section. Okay, so this is like you have 4 lines, and this green 4 lines are the mirror of these. Okay, so the region surrounded by these 8 lines. Okay, you just join them. They join up from one line to the intersection of the other line, and then from the other, and so this region should be no line should pass inside this one. If a line is passing inside this one, then there will be a problem. That will be just not a cone. Anything which is all the lines should pass outside this one. Okay, so all the lines, so the region should be inside all of these lines. Now, if you look to this point number 3, this line number 3, which is corresponding to the stress at this equal to 0. So this is not contributing. This 3 number point is not contributing in this line. And there is a reason that the stress, to make the stress at this equal to 0, okay, is not governing this cone of a section. Okay, because this is very near to this one. So if it is inside this one, then the stress automatically will be equal to 0. So this is outside. Okay, so this is not creating, all the line will not, all the boundary line will not make a part of the curve. Okay, so if it is outside, then leave it. Okay, so this is outside, so this is not taking a part. So in the case of T section, there is no need to take this point number 3. You should take point number 1, 2, and 4. Okay, just take these points and it will give you the kern of this T section. Okay. So I'll recommend that you should do this. You should do this calculation just to develop an Excel sheet, and I will recommend just to draw this figure in AutoCAD just to see actually and to get actually this diagram, because if you want to draw it with your own hand, then you can, because there's some, especially 1 and 2 line are very close to each other, so you can have an error in this case. So I'll recommend कि आप इसको CAD में करें. You know the CAD, how to use the CAD, so you should know and you should apply these things in CAD, AutoCAD, and draw this figure. This is drawn in AutoCAD. ठीक है ना, ये figure जो है AutoCAD में draw हुआ. So AutoCAD नहीं किया है क्या मतलब है? कब करेंगे आप AutoCAD? आपने drawing नहीं पढ़ा है? Have you not studied drawings?
Sir, only AutoCAD नहीं किया सर.
AutoCAD क्यों नहीं किया? ड्राइंग में नहीं था AutoCAD आप?
सर वो तो सर अभी फर्स्ट सेमेस्टर वालों को पढ़ाया गया, हमें नहीं पढ़ाया गया था.
हमें सिर्फ मैनुअल ड्राइंग पढ़ाया था.
नहीं तो आप कब, AutoCAD आपके कोर्स में नहीं है? आपका कब ये मैनुअल ड्राइंग कब था आपका? ये जो है वो क्या आपने कब पढ़ा?
19 सर.
कौन से सेमेस्टर था आपका?
फर्स्ट सेमेस्टर सर.
फर्स्ट सेमेस्टर में. और आपने AutoCAD बिल्कुल नहीं पढ़ा, टच ही नहीं किया?
सर सिर्फ इंट्रोडक्शन किया था आखिरी लास्ट क्लास में.
What was the reason? वो क्यों, मतलब एक कोर्स में एक चीज शामिल है तो इंट्रोडक्शन तो नहीं है ना, पूरा कोर्स शामिल है ना.
सर सिर्फ 20-25 मिनट इंट्रोडक्शन किया था और कुछ नहीं किया.
नहीं तो मतलब ये आपकी भी एक वो बनती है ना जिम्मेदारी की, एक कोर्स में, आपके कोर्स में तो शामिल है ना पूरा, मतलब उसमें जो है वो उसका अपना एक जो है वो CLO होगा, ठीक है ना, और उसके अपने जो है वो, मतलब ये तो इस तरह तो नहीं है ना कि चीज जो है वो विदाउट CLO का, फिर वो CLO का स्कोर जो है वो किस तरह मिलता है अगर आप उसको कवर नहीं करते.
पर तो फर्स्ट सेमेस्टर में तो हमें पता ही नहीं था कि क्या टीचर करता है, क्या बोल जाता है.
अच्छा चलो मैं इसको देखता हूँ, ठीक है, आपके कोर्स को भी जरा देखता हूँ और देखता हूँ कि ये क्यों जो है वो रह गया, ठीक है ना. बट यू कैन ड्रॉ ए बिग फिगर, कोई एक मतलब एक ग्राफ पेपर लेके उस पे जो है वो इसको जरा ट्राई करें, बट यू शुड, मतलब इसको ट्राई करें, और ये चीजें जो है वो जब रह जाती है तो फिर रह जाती है, ठीक है ना, फिर आपको जो है वो फिर इसमें मसला जो है वो होता है. ठीक है, मैं यहाँ पर स्टॉप करता हूँ. जो अननोन प्रिंसिपल एक्सिस है उसको मैं जो है वो कमिंग क्लास के लिए छोड़ देता हूँ, ठीक है. सो इंशाल्लाह कमिंग क्लास में हम इसको भी पढ़ेंगे और साथ में जो है वो अनसिमेट्रिकल बेंडिंग हमारा नेक्स्ट टॉपिक है वो पढ़ेंगे इंशाल्लाह, ठीक है. कोई क्वेश्चन आपका हो? इफ यू हैव यू कैन आस्क.
यस सर. सर
जी
सर ये हम जब मालूम करते हैं मोमेंट ऑफ इनर्शिया,
ओके,
सर तो मास भी एक बॉडी के फिक्स होती है, और सर रेडियस भी सर फिक्स होती है एक बॉडी की. सर तो फिर हम ये इस तरह क्यों लेते हैं कि समेशन ऑफ m एंड r स्क्वायर, सर ये क्यों लेते हैं हम?
समेशन ऑफ m and r स्क्वायर, तो वी आर नॉट डूइंग, हम यहाँ पर जो है वो m and r जो है वो नहीं करते बल्कि a and r करते हैं. जो हम मोमेंट ऑफ इनर्शिया कैलकुलेट करते हैं, दो मोमेंट ऑफ इनर्शिया जो है वो होती है, ठीक है ना. एक को मास मोमेंट ऑफ इनर्शिया जो आप कह रहे हैं, ठीक है ना, उसको मास मोमेंट ऑफ इनर्शिया कहते हैं, और एक है एरिया जो है सेकंड मोमेंट ऑफ एरिया या एरिया मोमेंट ऑफ इनर्शिया. ओके, तो हम क्यों करते हैं का मतलब एक देखें हम क्यों करते हैं, इसका जो आंसर है ना, इसका आंसर वो आपको जो है जब आप किसी फिजिकल फिनोमेना को डिस्कस करते हैं, यू कम अक्रॉस सर्टेन नंबर,
ठीक है ना। आपके पास लेट्स सपोज यू आर डिराइविंग समथिंग, जब आप उसको जो है वो, जब आप फ्लेक्सर फार्मूला को व्हेन यू आर डिराइविंग द फ्लेक्सर फार्मूला, तो फ्लेक्सर फार्मूला में एक टर्म आ रहा था इंटीग्रल y स्क्वायर dA, एक टर्म आ रहा था, वो वहां पर जो है वो ड्यूरिंग उस जो है वो उसमें आ रहा था, वो अपने आपके डिराइवेशन में आ रहा था, ठीक है ना। एंड यू नेम इट एज ए मोमेंट ऑफ इनर्शिया, आपने उसको जो है वो मोमेंट ऑफ इनर्शिया, सेकंड मोमेंट ऑफ एरिया का नाम जो है वो दे दिया। तो वो हम क्यों करते हैं, वो हम इसलिए करते हैं कि हमें जरूरत पड़ती है। हम इसके बगैर क्यों, हम हमारे पास हमारे एक्सप्रेशन में आई आ रहा है तो हम आई को कैलकुलेट नहीं करेंगे तो क्या करेंगे। मैं आपको क्वेश्चन अभी भी नहीं समझा कि मतलब, मैं तो आपने कहा कि हम जो है वो m भी फिक्स है और r भी फिक्स है, तो हम क्यों करते हैं, मतलब मुझे इसकी समझ नहीं आई। जरूरत होगी तब हम करते हैं ना।
सर इससे सर मैं इससे बाहर बात करता हूँ ना, कि जो
जी
आम
जी
जो होता है मास 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 इनर्शिया होता है सर, उसमें हम
हाँ।
क्यों समेशन लेते हैं सर, मतलब मास भी फिक्स है सर और रेडियस भी फिक्स है सर, तो फिर क्यों समेशन लेते हैं, इसका क्या मतलब है सर, मैंने एक बुक में देखा था इसलिए पूछ रहा हूँ।
नहीं मतलब आप उसकी बात कर रहे हैं कि कोई कंपोजिट सेक्शन है या जो है वो एक सेक्शन है, तो हम उसमें समेशन तो नहीं लेते ना। एक सेक्शन है तो हम तो सिंपल जो है वो, मतलब आपके पास इफ यू नो द रेडियस ऑफ gyration and if you know the mass of the section, so mr square will give you the mass moment of inertia of that section. ओके, या जो है वो एरिया है तो बस आपको एरिया जो है वो दे देगा। वो फिक्स का मतलब जो है वो फिक्स, तो मास फिक्स है ना और रेडियस फिक्स है ना, लेकिन मोमेंट ऑफ इनर्शिया तो एक क्वांटिटी है एंड यू नीड द मोमेंट ऑफ इनर्शिया।
यस सर, एक दूसरा क्वेश्चन ये है कि सर जब मोमेंट ऑफ इनर्शिया सर एक फिक्स्ड वैल्यू सही होता है ना
जी, किसी भी
सर, तो
क्रॉस
फिर
सेक्शन,
हम
पर्टिकुलर क्रॉस सेक्शन के लिए। हाँ
यस सर, तो फिर हम एक्स मोमेंट ऑफ इनर्शिया इन एक्स डायरेक्शन, वाई डायरेक्शन से जेड डायरेक्शन से सही क्यों पाए,
नहीं, फिक्स तो नहीं
एक ने
होती,
कभी
मतलब
नहीं।
फिक्स नहीं नहीं एक वैल्यू तो नहीं होती ना। मोमेंट ऑफ इनर्शिया अबाउट एक्स कुछ और फिक्स वैल्यू होती है, अबाउट वाई एक्सिस कुछ और फिक्स वैल्यू होती है, अबाउट एक्स एक्सिस कुछ और फिक्स वैल्यू होती है। हर एक्सिस के अबाउट जो है, जब आप एक्सिस को चेंज करते हैं मोमेंट ऑफ इनर्शिया की वैल्यू चेंज हो जाती है। मैं सिंपल सी मिसाल, लेट मी गिव यू अ सिंपल एग्जांपल। इफ आई एम गिविंग यू एज स्टील का एक प्लेट, आई एम गिविंग यू अ स्टील प्लेट whose dimension is 3 inches and 6 inches, okay, and I'm rotating it about a center. I have a mechanism. I'm rotating is about the center of that plate. Okay, so it will offer a resistance. I will have to apply certain force to rotate that plate. Okay, and it will offer certain resistance. Okay, which is actually proportional to the moment of inertia of that. Now, if I rotate that plate about one of the edge, अगर किसी edge के about मैं उसको rotate करूं, okay, so it will offer more resistance. Okay, it will offer, if rotating it about the edge, one of the edge will offer more resistance. Okay, so that's the reason that the moment of inertia about the centroid, about the center of that plate is lesser, and about the edge it is a high value. For area, this is bh square by 12. Okay, bh cube by 12, and at the centroid and at the edges, this is bh cube by 3. So the moment of inertia has a different value. You will have to study these geometric properties. I have given you just a brief introduction of the geometric properties. You will have to study these geometric properties in detail, how they are calculated. And the concept is simple. Why we are calculating? Because they are required in certain formulation. This is a simple thing. What is moment of inertia? Forget about the definition of the moment of inertia. This is a mathematical number. What is area? When if somebody is asking me that what is moment of inertia, then I'm asking him what is the area. ठीक है ना, एरिया को आप डिफाइन कर सकते हो. कैन यू डिफाइन द एरिया? आप जो है वो, आप अगर किसी चीज के साथ उसको एसोसिएट करते हो, सो इट्स ओके. ओके, हर केस में द डेफिनेशन ऑफ एरिया इज डिफरेंट. ओके, सो सेम इज द केस फॉर द मोमेंट ऑफ इनर्शिया. ओके, सो जो मैंने आपको बताया था कि वो भी जो है वो डिफरेंट है. सो समटाइम्स इट इज द रेजिस्टेंस, इट इज द बेंडिंग रेजिस्टेंस ऑफ ए मेंबर. समटाइम्स इट इज द बकलिंग रेजिस्टेंस ऑफ ए मेंबर. Okay, so there are different condition and different things. Okay.
Yes. सर
जी
सर ये एक और टर्म सर हम इसके बारे में बोलते हैं कि ये जो सर जहाँ जब एरिया मोमेंट सर एरिया सॉरी सर
for second moment of area.
ये सर ये वाला